Hello.
Hola, Cari, ¿cómo estáis?
¿Cómo? Bien, ¿y tú?
Bien, bien. Llegué justo para la clase.
Sí, eso te decía. Llegaste justito. Hoy estáis doble. Ten-
Ay, entré en la Andy. Sí, a ver. Ahí sí. Tenía que instalar Zoom. No sé por qué se me había desinstalado.
Uy, qué raro.
Mm. Oye, ¿descansaste?
Re poco, la verdad. Como que aproveché de ponerme al día.
Buena. Te toca a ti hasta PH como esta semana, ¿o no?
No, el 31.
Ah, ya.
Llegó el profesor. Hello.
Sí, hola, profesor.
Hola, ¿cómo estás?
How? Bien, ¿y usted?
Hola.
¿Cómo fue su semana de receso?
Bien. Sí, bien descansada por mi parte.
A mí
Yo
también.
necesito otra semana.
Sí, siempre.
Otro mes, otro mes.
Por favor.
Otro mes.
Sí, I'm feeling that too. So, oh well. Okay, you should have all gotten links,
Yes.
at
Thank
least
you.
a few things in there. I'm sorry they're not. It's not fuller. It's not a full Christmas yet. But the major things are there. So the exam is there. The first one or two homeworks should be there. Priscilla promised me she would upload 3 and 4 today sometime. Hopefully that happened or will happen. But it clearly didn't happen because it's not there. So,
Professor,
any
you
questions?
send that via email?
I just sent it like 10 minutes ago
Okay. I'll wait.
to your uc.cl account.
Okay. Thanks.
But yeah, I made a Dropbox link for everybody. It should have been the same, but I think I sent Laura the wrong one, and so I had to resend it to her.
Professor?
Yeah. Is it-
The number in the homework is the score, o sea, el puntaje.
For the homeworks, I need to check it. So it's still like Priscilla downloaded it, and she hasn't given me a full list of the grades. So I can check it for you afterwards. Yeah.
Ah, okay.
I think she didn't add up all the points, so they're individual points for each question.
Yo creo que el puntaje, no la nota.
Sí, todo es puntaje.
Yeah.
Todo es puntaje.
Okay.
Sí,
Okay.
sí.
Yeah, thank you.
No, because it's out of 20 something. I don't know. But it is fácil para convertir, ¿cierto? Yeah. Okay, good. Hola. Okay, so we almost have a quorum. So any questions, doubts? Did you all have a look over the pauta, the solution for the exam? No, you guys like no class, nothing to do with class. Okay. Well, anyway, have a look over it, see if you agree with my grades and everything. And yeah, we can discuss it. Okay. In terms of I mean, so I was trying to do a histogram, but I failed to do it. But the average score was a 49, let's see, 49 something. Yeah, 40 was basically 49 out of 66, which would have been in the Chilean units of 5.5. So not too bad. And the highest one was, I think, almost a 60 out of 66. Just to put yourself in scale. So not too bad, in my opinion. Okay. Hopefully you thought it was okay, fair, reasonable. Try to test everything that you had learned. Someone please send me the email.
I didn't get it. So
Okay. Yeah.
if anyone could.
No, it's individualized.
I haven't
Each
received
link,
anything either.
each link is individualized. I don't know what to tell you.
Okay,
Yeah, all of them.
I'll wait after class.
Yeah, basically they were all sent between 2:59 and 3:21
Okay.
to your UC email from my Gmail. So maybe there's an issue there.
Okay.
I see. Okay. Anyway, if not, we'll sort it out. Okay. Did anyone receive it? Let's ask that question. Did anyone receive an email with a Dropbox link in the last 20 minutes?
Yes.
Okay, so the last one received it, but the first one did. Yeah, we'll see. Okay, give it a little bit of time, I suppose. Okay, so what we have covered so far has been, done with the tests. We went through black body radiation, free emission, synchrotron radiation. And so now we're going to deal with Compton scattering, right? And so hopefully you guys have all seen Compton scattering. Here are the emails for the Dropbox link. See, I did send them. Okay, so Compton scattering. So you guys should be familiar with this, right? It was probably in several of your physics classes. So an incoming photon comes in and it interacts with this electron and gets scattered in some other direction. And there's the potential for this photon, sorry, the electron to absorb some of the energy, right? And so you have a recoil where the electron will gain some momentum and the photon will obviously have lost some energy and come away with a different frequency, right? So that's Compton scattering. And you can also have inverse Compton scattering where you can have an energetic electron and a not so energetic photon, and when they interact, it upscatters the light, right? So it's just sort of the inverse process. And so you guys are probably familiar with this one, which is the scattering of high energy radiation by low energy particles. This one is the scattering of low energy photons by ultra relativistic particles. And the interesting thing about this is that the photons will have a frequency boost, which is proportional, can be proportional to gamma squared. And of course, if gamma is very large, then you get a very huge boost in this frequency, right? So you can take radio gigahertz photons and you can scatter them up to X-ray energies, for instance. So this is the sort of scenario. You obviously have some momentum of the photon, which you can sort of consider as the photon energy divided by c, or you can relate it to this sort of wavelength, Planck wavelength. You have the momentum of the recoiling electron, which is just going to be the this energy squared minus the rest mass. And then you have the final energy of this photon, which will be the final frequency. And so the change in frequency or the change in wavelength, this delta lambda, will be related by this. Okay, so we can sort of take this and start from first principles. And so we have, if we have an elastic scattering or a coherent scattering where there's no exchange of energies, then this is just Thomson scattering, right? And so at low energies, where the photon is much less than the rest mass of the electron, basically what you have is that the initial energy and the output energy are the same, right? And you have a scattering cross-section, which is sort of dependent on the angle here. It has some normalization and then some angular dependence. And if you integrate over all solid angles, you end up with the Thomson cross-section, right? So this is, we already discussed this earlier in the class. And so this is the sort of standard picture. Now, if we talk about how this modifies when we are in a relativistic situation or in a quantum mechanical situation, we have two effects that come in. And one is the kinematics of the scattering process, which is what was handled here. And the other is the alteration of the cross sections, which is what the quantum effects will do. And so this thing will change somewhat. So we can think about this single scattering situation, and we can use the notation that's in Rybicki-Lightman. So basically, we no longer have an elastic collision. So the output energy of the photon is not equal to the input energy, and there's a recoil of the electron, right? And so if we have conservation laws of energy and momentum, basically we have the photon momentum here. So we have the initial photon momentum, which is just this energy divided by c, and we have the electron momentum, which is just the rest mass of, or rest momentum of the electron, and then 0. So the final photon energy will be E1, so it's changed somehow, and then the final momentum of the electron will have some energy, right, and some momentum. So we just have conservation of momentum here, and so this side has to equal this side. And likewise, we can say that if we sort of square this, we end up with this quality here. So the final energy of the electron has to be equal to the square of the final momentum has to be equal to this. Okay, so if we plug in all of our equations and we factor in a relation between momentum and energy this way, and this way, what we end up getting is that we have a relation between the input energy and the output energy of the photon, which is modulated by this factor here. And of course, we can see that this cosine factor sort of comes in from here. And so depending on the angle, we'll have some potential exchange of energy. And this is proportional to this energy as a function of the rest mass of the electron. So that should all be fairly straightforward. We've seen this before. So if we write it in terms of the wavelength, so just plugging this through and saying this energy equals h nu, or h c divided by lambda. Then we have, let's see, or actually, yeah, h nu divided by c equals h divided by lambda, etc. Then we can end up getting this formula here, and we have a shift in wavelength, which is proportional to this cosine factor and this factor here, which is known as the Compton wavelength, which is just our constants using the electron mass. And we could do the same thing for a proton as well. And so typically the correction is ignored for Thomson scattering because the wavelengths here are typically much larger than this Compton wavelength. And so the only issue is when you get wavelengths which are very, very small, then you have energies which are very large. And so you actually start to have energies equivalent to the rest mass of the electron. So the other effect here that we basically have is that a classical electron cross-section is no longer going to be valid when we have very large photon energies. And so the cross-section will start to diminish a little bit for these high energetic photons. And so this correction is known as the Klein-Nishini formula. And so this cross-section as a function of solid angle now becomes something a little bit uglier, and it's related to the input and output energies, as well as our angle with which we're scattering. And so, you can see that there's actually, relations on both sides here. So there's the ratio of the input to the output and the output to the input. And so depending on what these are, one will dominate over the other. And so you get an interesting sort of proportionality. So if we sort of summarize this energy as a function of the rest energy of the electron, so to sort of normalize it with this X value, then the total cross-section, if we want to integrate this over all solid angles, ends up being this very pleasant looking equation here. And so we have multiple factors that come in from each of these. So if this is very, very small, basically the photon energy is much smaller than the rest mass, then this thing reduces to something which looks like this, and this is the non-relativistic case, and it should approximate this thing here. However, if we go to the ultra-relativistic case, where this is much larger than 1, then we get something which looks like this. And so we have a cross-section which ends up being smaller than this nominal cross-section in the Thomson regime. Okay, so those are, that's Compton scattering for you. And so this thing, it was never isotropic to begin with. And so we always had a front-back symmetry. This is the Thomson scattering case. So basically the photon is relatively weak compared to the electron rest energy. So the kinetic energy imparted to the photon is nothing. You get a scatter at some angle, and there's a probability which is higher here and higher here than it is here and here. And so just to show this, this is normalized units, and this is the scattering angle. And so when x equals 0, right? So when basically the photon energy is very, very low, you get something which looks like that. And then as you increase the photon energy towards the rest mass, you end up getting something which is front symmetric, or it's no longer symmetric. It's a forward scattering centric sort of probability. So something closer to x equals 10 here is shown here. And you can see that the probability now is very dominated by this forward scattering component. And you also impart some energy to the electron, shown by this blue arrow. Okay, so that's that. So we can think about the Compton scattering in either the photon frame or in the electron frame. And so if we think about it in the electron frame, then basically we will do a Lorentz transformation to go from our input energy here to the energy that the electron sees in its frame. Right? And so this conversion here is going to look like that. Right? So it's our sort of standard Lorentz transformation. Then once we have the scattering take place in the electron frame, there will be an emitted photon, which would be E'1, and we want to transfer it back to the original frame, the original photon frame. And so there we would again have a transformation and transform it back like that. And so our original relation here in the photon frame, when we transform these and plug these in, we end up with something which looks like this. And what's interesting about this is that in this particular frame, this thing appears to be small. And so basically, so even if this this energy here was whatever it was, and we have a boost by gamma, whoops, but we have this other relation here, and then we have this other transformation. And so this thing here ends up being this kind of mess of a thing. But ultimately, this, for modest terms of gamma here, this ends up being small. And so effectively what this ends up being is that this is almost equivalent to this energy. And if this is the case, then this, in the electron frame, this scatter appears like a Thomson scatter, which is a little bit weird. But all of the sort of shifting here comes from these transformations. And so in this particular case, and this is a sort of middle regime in between the Thomson scattering case and the ultra-relativistic case, this thing holds. And so this is relatively small. And so there's not a huge difference between these two. In terms of the angles, going from the K frame to the K prime frame, you go like this, and you would transfer, from E to E1. In the primed frame, what this looks like from the electron point of view is that you have an incoming photon going in this way, and then you have an outgoing photon going in this way. And so you've transformed the angles, you've transformed the energies. And basically what happens is you get a Doppler shift here, you do a Thomson or a Compton scatter, depending on whether this term is small or not. And then you do another Doppler shift back. And so far we haven't done anything too strange other than just change our reference point. Right? And so what happens here? So what ends up happening is that we end up having a couple of possible limits depending on how the angles affect things. And so we can consider a couple of different cases of so this is the incoming angle and the outgoing angle with respect to some reference frame. Right? And so basically this sort of conversion here is related to this and this. And so we can think about these limits as they relate here. And so if we have a case which is pure front reflection, so the electron is moving in this direction, the photon comes in and it's red here, and what you're going to end up getting is that this comes in, it's 0, and then this is going to go out and it's going to be 90. But so you end up with something here that is that right? Actually, okay, this is 0. No, it actually goes out 0 too. So then this is 1, and you end up with something which looks like that. And so you can rearrange these things to get something which looks like this. And of course, this is simply just this ends up being equivalent to 1 + 1 = 2, right? 2 squared = 4. And so we end up having a boost for front reflection that is a proportion about 4 times the gamma squared. We can also consider the case of back reflection. And sorry, actually, I give the angles here. So this is actually 180, this is 0. So the back reflection is the opposite. So this is coming in, and so this is 0, and then going out, it's pi. And so plugging those in again, you get something which looks like this. And you can then kind of couple these up again, and you end up with, again, something which looks like that. But now gamma here is gamma to the -2, not gamma squared. And this thing, again, is 2, but then it's 1 over 2 squared. So it's 1/4 gamma minus 2. So there's a huge difference between front reflection and back reflection for this Compton scattering, right? So in this case, you have a photon which gets upscattered by a factor of 4 gamma squared. In this case, you have a photon which gets downscattered by a factor of 1/4 and then gamma minus 2. And so you have a huge energy deboost here. You have a huge energy boost here. You can also think of a situation where you have some sort of photons which come in from all sides. And so they will end up coming in. And so this is an isotropic field, right? And so this electron, when it sees it, it's going to see everything as being beamed towards it, right? And so because it's moving, it's going to see a very narrower sort of regime. And when it does its scattering, the scatterings are all going to be preferentially upscattered in this direction, but with some sort of angle here. And so the sort of intermediate case would be an incoming photon comes in like this, and what happens is the outgoing photon will leave with an angle which is proportional to the beaming angle, 1 over gamma, right? So it comes in here and goes out like that. And in that case, the energy boost will be roughly proportional to this, or roughly proportional to gamma squared. And that's going to be the sort of package, right? So you get a very different boosting depending on how these photons are coming in. And we can ask, you know, how likely are any of these situations to occur? What happens to the typical photon? And then what would a spectrum look like after this interaction with a single electron? And so if we had a photon field and it was interacting with the electron, what would the outcome be? What would the output look like for us? And so hopefully we'll answer some of these questions in the next 10 minutes, 20 minutes, or next class. Is everyone following me so far? Is everyone on board? Any questions? Okay. Okay, so we can think of this as the following. So we have the first step, which is an electron is moving through an isotropic radiation field, right? And has a very high speed. And so when we do our Doppler shift between these two things, we're going to have in the electronless frame, all the photons are going to appear to come from an angle that is 1 over gamma, right? And then in the second step, basically we have all these photons coming in, and we want to have an interaction between the photon and the electron in its rest frame. And so the electron is now at rest, the photon is coming in, and so depending on how this energy is, if this energy coming in is less than this, we're going to have a Thomson scatter. And so if it's a Thomson scatter, then the probability will look like this, right? And so we'll have a slight preference for forward-back symmetry. And so if they're all coming in this way, then we should end up with a distribution which is roughly like that, right? And then we want to shift that back into the photon frame again. And so when we shift it back, all of those photons which are going in all directions end up being beamed in this direction, in the direction of the electron, right? So even though in this intermediate step, we've totally not totally, but we've actually isotropized a lot of these directional photons, but because of this step, we've beamed them back in the original direction. Or not the original direction, but we beam them back in this direction. So it's a little bit interesting. Right? So the whole idea here is once you have an electron that's in a moving frame, an electron that is not at rest, you have to do this Doppler, or not the Doppler, the Lorentz transformation between the two frames, and you get this extra sort of effect here. Okay, so basically we have double beaming, and more photons end up being upscattered than backscattered because of this. First of all, this sort of front-back symmetry. So there is a probability that they will come here or here, and then many of these will then be beamed in this direction, the forward scatter direction. And even the ones that are going backwards, some of them will be beamed in the forward direction, right? And so you get a predominantly forward scattered output. So coming back to these questions, what's going to happen to the typical photon? It's going to be forward scattered. And it's going to have its energy bumped up by a factor of gamma squared, typically. And the photons that are backscattered, there are going to be very few of them, and they're going to be less energetic. And so if you're looking at a specific frequency, right, you're going to be dominated, particularly if it's high frequency, you're going to be dominated by photons that have been forward scattered. Okay, so that is Compton scattering in some detail, and then dealing with the Lorentz transformations. And so we now have a case where, let's say we have relativistic electrons. So this situation holds where basically they're traveling at a speed which is much larger than the photon that's in the field relative to the rest mass of the electron. And so here the energy before scattering is going to be very small. And then when you shift it into the electron frame, you're going to have a shift of a boost of 1 gamma. And then you're going to scatter it. You could potentially then, it will behave as a Thomson scattering because the energy is not very high. But then when you when you length transform it out into the photon frame again, you're going to have an extra factor of gamma here. And so what happens is you've upscattered that photon by a factor of gamma squared, right? And so this, of course, only holds when you have the condition of Thomson-like scattering, meaning that in the frame of the electron, this condition is met. So the gamma times this energy must be less than the rest mass of the rest energy of the electron. And of course, then you have another case where this doesn't hold, and then you actually have to deal with the energy transfer in the electron frame before doing the two transforms. Does that make sense to everyone? Hopefully. Okay. So this is a nice way of taking, if you have a relativistic group of electrons, distribution of electrons, and a photon field, it is a potential way of transferring some energy from the electrons to the photon field, right? And so this electron distribution will take a low energy photon and convert it to a high energy one with this boost. And so if you have electrons that are in, say, a relativistic jet, and they have a gamma of 1,000, 10 to the 4, to 10 to the 3, or 10 to the 4, right, then that's going to be 10 to the 6 or 10 to the 8 in terms of the boost. And so as I had mentioned earlier, you can take a radio photon, which is 1 gigahertz, so 10 to the 9, and you boost it by a factor of 10 to the 8, and you have 10 to the 17, which is now in the X-ray regime. So basically, an intermediate, the intermediate photon energy in this case will still be relatively small compared to the rest mass of rest energy of the electron. And so you can still do that. In fact, you can generally take photons, as long as they have a limit of, say, 100 keV in the electron frame, they're going to be fine. And so you can take optical photons with a gamma of sort of 3, and you can upscatter those, and those will then upscatter. That's 10 to the 14. This would be 10 to the 3 times squared, so 10 to the 6. So you'd have something like 10 to the 20. And so you get a gamma ray photon. And so the output energy can be much higher than the rest energy of the electron, right, because of this gamma effect. As I mentioned, if the intermediate energy ends up being too high, then you have to deal with the relativistic and quantum effects that come into play. And the trick there, of course, is then that you don't have Thomson scattering. You have to deal with a Compton scatter in the electron frame, and you have to deal with the potential decrease of the cross section due to the Klein-Nishini sort of formalism. And so this, then you have something where you reduce the effectiveness of this process, and you make this energy here less than this energy, and you also reduce the probability of the scattering to begin with. And so kinetic effects alone can limit the energy that ends up being achievable by the output photon that you generate. And so from energy conservation, you have some limit which might look like this. So it's this output energy in the photon frame has to be less than this combination input energy and the rest energy of the electron times gamma. And so basically for a fixed energy, the photon energies can never be larger than this. The output energies will never be larger than about this. Okay, so that's just the single scattering version of this. And so now we could look at how we would see this if we had, say, an isotropic distribution of photons scattering off an isotropic distribution of electrons. And so then you would average these different components, right, averaging over the solid angle that's seen here. And so we can think about an initial photon density. So we have initial phase density and P for the incoming photons. And so we have some sort of velocity is a function of energy here. And this is going to be, well, should that be velocity? No, I think this should be frequency. I can never tell these things apart. So some frequency as a function of energy, and it's going to have some number per sort of phase space, cubic phase space here. And this thing should be Lorentz invariant as follows. So VDE divided by E will equal V prime D prime, DE prime divided by E prime. And this should be invariant. And so we can think about the power in the electron frame here. And so this is going to be equal to DE prime 1 here divided by DT prime. And this would just end up being an integral over our infinitesimal energies of this frequency and of this energy in the electron frame. And we also have some sort of normalization here, which is the cross-section, the total cross-section. And if we wanted to do this in any particular direction, we would average it. Okay, so we can then assume that a change in the photon energy here in the rest frame will be negligible. And so this dE prime E1 dt prime should roughly equal dE1 dt. And this should be the case for as long as this holds. So this photon energy is less in the electron frame is less than the rest mass, much less than the rest mass. And so if this thing holds, this is the Thomson scattering limit, right, then we can just plug in that this thing here, we can plug in this version, and we now have sort of E prime squared here and that 1 over E here. And this thing is, of course, this. And so we can plug in that because it's invariant. And so we have this energy here as a function of time looks like this thing. And so it's this scattered cross-section, or the integral over the scattered cross-section, and then this integral here. And then we can also play our game with this transformation between E prime and E. And so we had, in the photon frame, we have this conversion here. And so we can plug that back in, right? So that what that is going to end up giving us is just that we have, let's see, going back here. So we have 1E here, which is sort of normal, and we have the E prime squared here. So we need to square this thing or square this thing. So we have a gamma squared, which comes out. We have this thing is squared, and then we have 1 energy here, and we've gotten rid of 1 energy here. So we've crossed that out. And so we now have this sort of equation. We have our gamma squared here, which kind of magically comes about. If we want to average over the angle, right, this is now based solely in the K frame, the original frame. And if we have an isotropic distribution of photons, we average over this, this angle here, and this in the average is roughly equal to this. And so generally speaking, the average of cosine theta is 0. The average of cosine squared theta is 1/3. So that's where we get this from. And so on average, this energy will be, this sort of change in energy here will be related to this here. And we can, in this sort of integral, when we do this averaging, we can just say that this is the initial photon energy density. And so this thing here, this integral, we just say this is the photon energy density. And so we have something which looks like this. And so the change in the photon energy density will be related to the cross-section, gamma squared, and then this extra factor here of beta, which, if this is relativistic, this will be close to 1. And so we'll have something like 4/3 times this. Okay, so what this will, of course, end up doing is you will have a rate of decrease in the initial photon energy density. So every time you get an upscatter, you don't have that available to use for your initial photon energy density. And the other thing, of course, you need the low energy photons in order to upscatter. Once you have a high energy photon, then you may it may not be in the same regime for Thomson scattering to apply any electron frame. And so basically it will have a much harder time of upscattering, or may even have so much energy that it might be kind of equitable with the electron. And so you won't get much of an upscatter. So the rate at which these fall out will be related to this. Right, so this is just counting the number of them. And so the net power lost by the electron will be the difference of these two things. And so it will end up being this thing here. Everyone still with me? Hopefully. Okay. we have this relation, and so we can substitute in here a little bit. Whoops. And so we end up having basically I keep going backwards. Right, so we have this thing, and so we have gamma, let's see, gamma squared minus 1 is roughly equal to this. And then we also had 1/3 beta squared and times gamma, which was here, right? So we had 1/3 gamma squared beta squared. And so when we combine them, we have 4/3. And so the power coming out from this inverse Compton scattering process will be proportional to this. And what's sort of interesting is that many of these factors here are similar to the power that came out of the synchrotron radiation, right? So the power from synchrotron looked like this. And so you had all of the same factors here, except for you're talking about the energy from a magnetic field, not the energy from the photons. In this particular situation, we are neglecting the electron energy transfer. And so if we account for this, then there's a modification here, which is this factor here. And so depending on exactly how much energy ends up being transferred, you have this extra factor here. But in general, this, depending on the situation, this just falls away and you end up with something close to this. So the ratio between these ends up just being the ratio of the energy density of the magnetic field to the energy density of the photon field. And so what does this really mean, if anything? So basically, if you have radiation losses due to synchrotron, right? So you have a relativistic electron population, which is radiating via synchrotron, and you have a photon field, then you could potentially have competing processes for how the electron loses its energy, right? Which depends on the ratio of the magnetic field energy density to the photon energy density. And this thing, holds basically for any electron velocity, because the beta squareds fall out, the gamma squareds fall out. So it's not just an ultra relativistic one, but it holds sort of everywhere. But it doesn't necessarily require any validity of the Thomson scattering and the rest of it. This should hold. And so you can, by sort of knowing you have a population of relativistic electrons, you can estimate how, in what process they will lose energy faster. Would it be from a radiation field, for instance, the cosmic microwave background, or would it be from the magnetic field, which is in the jet? And so it might depend, right? If you don't have a strong magnetic field, if the magnetic field energy density is sort of galactic, a few microgauss, and you have a high photon field, for instance, the CMB at redshift of 6, where the CMB is now, universe was not, less expansive, and so there's more photons. And so you get that competing process where you might actually have at high redshift photons losing energy, electrons losing energy via inverse Compton rather than synchrotron. Or if you have some other photon field nearby, which is very, very intense, you can have energy loss in that way. Does that make sense to people? Any questions? Okay, I think I'm almost done. One or two more slides. Okay. So these formulas obviously were dealing or sort of centered on single specific electron energies, gamma. And so the more general case is that we have a distribution, a power law distribution perhaps, right? So we have n number of electrons per gamma. We have some total energy involved, which is related to the amount coming off of the power coming off of each photon with some field, the number of electrons, and over this small chunk of electrons, which we're going to integrate. Right? And so we could have a power law distribution like we had before for the synchrotron case. And so in this case, we would have n equals this between this small range and 0 otherwise. And then we would piecewise integrate it. And in that case, the total power coming out would be related to our photon energy density, Thomson scattering cross-section, C 4/3. And then we have this component C, which is coming from the normalization of the electron distribution, right? How many electrons there are effectively. And then a relation that is dependent on the slope. And this dependence goes as 3 minus P. And so depending on the slope, you might have, if the slope is, this 0.7, which is what the slope is for cosmic rays going around the disk of a galaxy, then this would be gamma of roughly 2, right, 2.3. If you have a gamma which is flat, like in a radio jet, then P would be roughly equal to 0, and then you'd have gamma to the 3rd power, right? So you could have a much higher power coming out from that. The other case would be a thermal distribution. And so here, the distribution of the electrons would just go as some temperature, right? So some thermal distribution. Obviously, you need to have them be fairly energetic. So they have to be relativistic. So it has to be a relativistic distribution, which is why it's 3 kT here, because it's a Bose-Einstein distribution. And you have to have gamma sort of not really, really high, but still decently high. And so in this case, then the power coming out would look like this. So it would end up basically being 4 kT divided by the rest energy of the electrons times this and times the number of electrons. And these are kind of the 2 cases that you might most commonly come into contact with. This would be either for cosmic rays in the disk or a jet. This would typically be for electrons which are very, very hot still, right? So you still need them to be of order, sort of 10 to the 8 Kelvin or so, or in terms of keV, of order 10 keV or so. And then they can upscatter things. And of course, the classic situation of this is a cluster of galaxies where you have X-ray, emitting Bremsstrahlung component, which is a thermal distribution, right? But the temperatures are 10 to the 10 keV or so, or 10 to the 8 Kelvin. So they're very, very hot, but not super relativistic. And of course, then the photon distribution comes from, say, the C and B. So it's a very low energy, and you get an upscatter. And this shifts the distribution by a little bit, right? And so towards a cluster, you end up seeing that the spectrum of the C and B is distorted, which is known as the Sunyaev-Zerdovich effect, which we'll come back to when we talk about examples. Someone had a phone call. Okay, so basically this is the total power that comes out. And now the next step is to actually look at what the spectrum looks like. And so one of the key things, obviously, we've gone through this process from a single electron to a single electron with a photon distribution, and then a photon distribution and an electron distribution. And so obviously the spectrum that comes out of this will be very dependent on both the energy distribution of the incoming photons and the energy distribution of the electrons, right? And so it will be very case dependent. And there's sort of only specific cases that we really will be able to look at in detail. Okay, so that's all I really wanted to say. Any questions about this first part? Or questions in general? Did you guys get emails yet? Okay.
Yeah, I think I'm maybe having some problem with my email because I haven't got anything yet. I've been checking and there's nothing there.
Yeah, no, it's strange because we got an email.
Yeah.
And I don't know if anyone else did. But I will, if not, I will try again
Okay.
soon. But yeah. Okay. I don't know how to demonstrate that
No,
Yeah.
I definitely believe you. But if I got it, I would respond like, "Hey, I got it." If not,
Yeah.
I'm still waiting.
here's your link. So yeah. Okay. Any other thoughts? No.
A
Okay,
mí tampoco me ha llegado el correo.
¿Qué cosa?
Tampoco me ha llegado el correo.
Ok. No sé por qué. Es un problema con los correos WhatsApp.
Sí.
No sé si es un problema entre Gmail y UC o es solamente dentro de UC. Pero voy a probar. Ya. Y quizás, no sé si, no tengo correos afuera de UC para todos. En algunos casos sí. Y puedo mandar un enlace por eso. Pero sí, es un poco extraño que tú has recibido esto, nada más. So yeah, okay. What else? Nothing? Okay. Okay, well then I guess we will talk to each other on Monday, or sorry, Wednesday, miércoles, and we'll pick up where we left off talking about the spectrum. Okay? Okay. Ciao todos.
Ciao, ciao.
Bye.
Chao, profesor. See you Wednesday.